In this video, we're going to talk about subspaces and span. We'll do a quick review of linear combinations and linear dependence. We'll talk about a subspace, which is essentially just a subset of a vector space that also happens to be a vector space. And then we'll talk about span. And span is sort of, I like to think of it as if you have a set of vectors, the span of those set of vectors are the vectors that you can make. So it's kind of like if you have those colors as vectors, if you have a set of colors, maybe it's red and blue, then you want to know, well, what colors can I make from that? And generally you would say purple, red, and blue, dark blue. So again, that's the idea of span, but we'll look at it in terms of definitions of linear algebra. I also want to mention topics that are important that are not covered, which is the null space, the range, and row and column spaces. We will start by reviewing the definition of linear combination and linear dependence because it's so central to so many things we do in linear algebra. So a vector y is a linear combination of these n vectors, which will designate v1, v2 up to vn, if there exists scalars, one scalar for each vector, such that y is equal to the sum of scalar multiples of each vector. So each vector we scale with a scalar multiple, and then we add all the vectors up. And then y would be, this is a linear combination when we scale the vectors and we sum them. Then we have the definition of linear dependent and independent. So a set of vectors is linearly dependent if there is a non-trivial solution to this equation here. So it's a linear combination of your vectors and you set it equal to 0. So if they're scalars, a1, a2 up to ap, that will satisfy this equation so that the linear combination is equal to 0, your vectors are considered to be linearly dependent. And if you recall from our last video, if they're linearly dependent, that means you can write one of the vectors in terms of the other ones. So for example, I can write v1, if I subtract all these vectors to move them to the other side of the equation, and then divide by a1, I will have written v1 in terms of all the other vectors. They are linearly independent if there's only the trivial solution here. So the only way you can get, you can scale all the vectors and sum them together and equal to 0 is if a1, a2 up to ap, they all have to equal to 0. And remember also, if they're linearly independent, that means you cannot write any of the vectors in terms of the others. You cannot construct any of these vectors from the others if they are linearly independent. I wasn't really going to talk about subspaces, but then the word subspace is all over the place, so I thought I should at least define it. So it's actually a pretty easy concept. So V and W are real vector spaces. So if they're vector spaces and W is a subset of V, a non-empty subset, then W is a subspace of V. So it's a vector space, but it happens to be contained in V, so it's called a subspace of V. One of the interesting things about subspaces is if you start with W and you know it's a subset, you don't know if it's a vector space itself yet, but you know it's a subset of a vector space V. Then if you want to show that W is also a vector space and therefore a subspace of V, you only need to show these three properties. And the reason why that's interesting is because usually when you want to show something as a vector space, you have to show all 10 properties. But the thing is because you know V is a vector space, and you know for any two vectors in V, the commutativity law is satisfied, then you know since W is a subset of V, then you also know any two vectors in W will satisfy the commutativity law. It'll also, that's true of any three vectors in W will satisfy the associative law because W is a subset of V. You also know all these scalar multiplication properties will also hold because they hold for any vector V. So what you're left to having to show for W being a vector space is first, the 0 vector is in W, that's here, the additive identity. You have to show addition is closed, so this one you still have to show, and scalar multiplication is closed, and that's this one. You'll get this for free because if you have the additive identity, then you have to have the additive inverse because it's closed. So these are the only three properties you need to show. if W is a subset of V, to show that W is also a vector space. A quick example, because now that we're talking about it, I can't resist. So let W be the subspace of R3. So we know R3, we talked about this, we showed this in the last video, is a vector space. We want to verify that W is a vector space when W is equal to the vectors where x1, x2, x3, such that x1 is equal to x2 minus x3. So kind of writing that out, you have vectors that look like x2, x3, and x1 is equal to x2, x3. So one example is x2 is equal to 3, x3 is equal to 2. That means x1 has to be equal to x2 minus x3 is 1. And my claim is this set of vectors, all the set of vectors that look like this, form a vector space. And the three things I need to show is, one, the 0 vector is in W. So first I have to show 0, 0, 0 satisfies this condition of being in W. But that's true because x2 minus x3 is 0. So we have that 0, 0, 0 does satisfy the condition to be in W. Next, we have to show that addition is closed. So if we have two vectors, we'll call them vector A and vector B, such that, and both of these vectors are in W, so A1 has to equal to A2 minus A3, and B1 here has to equal to B2 minus B3. When we add these two vectors together, we get A2 minus A3 plus B2 minus B3, and then we have A2 plus B2, A3 plus B3. And then looking at this first component, this top component, which is A2 minus A3, B2 minus B3, we want to know, is this first component equal to the second component minus the third component? So here I have the second component minus the third component, and you can rearrange the terms, and you see that these two are equal. So again, here we see that when you add two vectors, its form is still in W, so addition is closed. Last, you can do the scalar multiplication is closed, so you multiply alpha times x1, x2, x3, where x1, x2, x3 is equal to alpha x2 minus x3 on top, alpha x2, alpha x3. We can pull out this first term, alpha x2 minus x3, and then we can compare that. This first term has to equal to x2 minus x3, so we pull out the x2, we pull out the x3, and we see these two are equal. So we have verified scalar multiplication is closed. Therefore, W is also a vector space and is a subspace of R3. Now we are ready to talk about span. So we have this theorem, and I tend to name my theorem in parentheses and then state the theorem, but here they sound the same. But essentially the theorem says that the set of all linear combinations of a set of vectors is a subspace of Rn. So if you have n vectors, and we'll call that set S of n vectors, then the set W consisting of all linear combinations of the vectors is a subspace of Rn. So remember, the linear combinations look like this. So if you have n vectors, then all possible linear combinations that look like this. So different, basically the same vectors, but different coefficients. So all possibilities, the whole group of all these linear combinations is a vector space according to this theorem. And then we call that subspace W, consisting of all linear combinations, as we call it the subspace spanned by S, or for short we just say it the span of S. And we denote it with span of S, or span of, and then we list out the vectors. And I have two examples for you. We'll do them worked out. But the span of a single vector is a line, and the span of two linearly independent vectors is a plane. Our first example is the span of a single vector, and we see that it is aligned here. So for example, if our vector is equal to 2, 1, we want all linear combinations of our vectors. Well, there's only one vector, v, is equal to 2, 1. And all linear combinations means we're going to multiply it by all possible scalars, a1. So if we multiply this vector by 2, we get this point. If we multiply by 1 and 1/2, we get something like this. Multiply by half, we get this point. Multiply by negative, and we get this point. But you can see that all of these points we get as we scale v, we have this point on the line. Our second example is the span of two linearly independent vectors is a plane. So here's an example, u and v. These are linearly independent, and the importance here for the two vectors is they are not collinear. So it's not it's not like u plus this blue vector here, which is really very much the same vector as u, except shorter. I had talked about the span of a single line, so if we consider multiplying u times all the different scalars we can have, we're just going to extend this line here, and when we multiply by negative in scalars, we're going to extend u this direction, whereas v, as we multiply by scalars, positive scalars, we extend v out this way, and by negative v, we extend v out in the opposite direction. I have covered this example in a little more detail in an earlier video. It's sort of supplemental about kind of some examples on giving intuition behind vector spaces. So I'm going to cover this very briefly in this video. So I've extended v, I've extended u, and the idea is now when we add different scalings of u to different scalings of v, we'll get the whole plane, the entire plane. So for example, just starting with u plus v, and we just use our parallelogram law, we will get this point here. When we scale u with something a little bit shorter than u, and scale v with something so that we have a vector a little bit shorter than v, then we get a point inside this parallelogram that's defined by the two vectors u and v. When we scale u over here by something a little longer than u, and scale v by something a little longer than v, then we're going to start to extend basically our parallelogram, and then we'll get something out here. Next, we'll take something a little shorter than u, but something longer than v, and we get this point over here. So essentially, what we're doing is by taking positive scalings of u and v, is we get all of this kind of quadrant of this plane. When we do something similar, adding negative v to negative u, we're going to get this quadrant of the plane. When we take negative v with positive u, we'll get this quadrant, and finally, negative u and positive v will get this quadrant. So all possible scalings of u added with all possible scalings of v is going to give us the entire plane, or an entire plane. So why do we need the vectors to be linearly independent? Well, collinear vectors do not span a plane. They just span a line, because if this is collinear, if u and this blue vector are collinear, we're not going to span a plane with that. We're just going to span a line. So if two vectors are linearly dependent, so a1v1 plus a2v2, what that tells us is we can solve for v1, and we see that it's just a rescaling of v2. So in other words, linearly dependent, two linearly dependent vectors are always collinear. So next we have this larger example. Let's say u is equal to 2, 1, 0, and v is equal to 0, 1, 2. We want to determine the span of u and v and give a geometric interpretation of this span. By definition, my span is equal to all the linear combinations of u plus v. So if I name my scalar multiples x1 and x2, it's x1u plus x2v, or written in vector form, looks like x1 times my vector plus x2 times my vector v. So in other words, w here, this vector w, is in the span if this part of the equation, this matrix A, which comes from these two vectors, u and v, times the vector x, you can verify. This gives you the same as this linear combination here. If you can find x1 and x2, that solves this matrix equation. And we can solve this equation by looking at our augmented matrix, which is row equivalent to this matrix here. So what this tells us is 0 is equal to 1/2 w1 plus w2 minus 1/2 w3. And now, just so that I can see this as an equation of a plane, first I multiplied everything by 2, and then I put my w's. I made w1 equal to x, w2 equal to y, and w3 equal to z. So w is equal to x, y, z, because people are just used to seeing this more readily as an equation of a plane than this. So again, W1 is equal to x, W2 is equal to y, and W3 is equal to z. And I said, and as I had mentioned, this here, if you remember what an equation of a plane looks like, it defines a plane. One more piece of terminology for you is the idea of a spanning set. So if you have a subspace of Rn, and S is a set of vectors, it's a subset of W, we say that S is a spanning set for W, or S spans W, if every vector in W can be expressed as a linear combination of S. Here we have W is equal to, so every vector W in your set, capital W, is equal to a linear combination of these vectors W1 up to Wm. Another way to express this is the span of S, and now we're using this notation, right? The space spanned by those vectors, which is called the span of S, is equal to W. These three terms are all three different kind of views of the same definition. Again, the span of a set of vectors are all the linear combinations of them. And if all the vectors in W can be expressed as a linear combination, then we say the vector spans W. A quick example, so if S is equal to the standard basis E1, E2, E3, and if you remember the standard basis E1 has zeros everywhere except in the first coordinate. E2 has zeros everywhere except in the second coordinate because it's E2. E3 means it's going to have zeros everywhere except in the third coordinate, etc. So we say that these three vectors span R3 because any vector v in R3, let's just say the vector v is equal to ABC, can be expressed as a linear combination of 1, 0, 0, 0, 1, 0, and 0, 0, 0. In particular, it can be expressed as A times R1, 0, 0, B times R0, 1, 0, and C times 0, 0, 1. So again, these standard bases, these three vectors, will span R3. Our next example is now we have these three vectors here, and my claim is U1, U2, U3 also span R3. And to show that it spans, we have to show that any vector in R3, we'll just call it V, and it's equal to ABC, can be written as a linear combination of these three vectors. And to do that, we would be solving the vector equation AX equals V. And here is our augmented matrix. Our matrix of coefficients are our three vectors, and then our ABC is this vector V here. It's row equivalent to this matrix, which tells us, and let me just write that, this is x1, x2, x3. It tells us that 1 times x3 is equal to minus a minus b minus c, that 2 times x2 is equal to a plus b minus 3x3, and x1 is equal to a minus 2x2 plus x3. So these are our equations. And essentially, once you plug in a value, once you know what a, b, and c are, that will give you, so right, we solved it for any vector a, b, and c, but let's just say, so if our vector is 1, 2, 3, then once we have our vector v, then we can figure out what these coefficients x1, x2, and x3 must be in order to write ABC as a linear combination of these three vectors. So what we do is we can say now that the span of U1, U2, U3 is equal to R3. It spans the whole space of R3. For comparison, we have this example. We have three vectors, and we want to know if it spans R3. Again, does it span R3? We want to know if every vector V can be written as a linear combination of these three vectors. So we take the vectors, we put them into our augmented matrix with the ABC, that's V. It's row equivalent to this matrix, and what we see, and this is x1, x2, x3, this only has solution, well, looking at this, 0 x1 is 0, 0 x2 is 0, 0 times x3 is 0. So it only has solution if 0 is equal to minus 7a plus 2b plus c. In other words, a, if I solve in terms of a has to be equal to 2/7 b plus 1/7 c. So there are many vectors a, b, and c which can't be solved. For example, the vector 1, 1, 1. In this case, a does not equal to 2/7 b plus 1/7 c, right? If a did, a should be equal to 3/7, but it's equal to 1. So this vector cannot be expressed as a linear combination of v1, v2, and v3, and therefore v1 and v2, v3 do not span R3. In this video, we did a quick review of the definition of linear combination and linear dependence. We talked about subspaces. So if you have a vector space V and W is a subset of V, but W itself is also a vector space, then we call W a subspace of V. Last, we talked about span. So if you have a set of vectors, V1, V2 up to Vn, then the span of these vectors is all sets of linear combinations of your V1, V2 up to Vn. So here, it's the set consisting of all linear combinations. So that's it for this video. We're well set up to go on into bases and dimension, which is a really important topic. Thank you for watching.